Welcome back to the Deep Dive. Today we've pulled together a huge stack of sources, textbooks, RFCs, you name it, to zero in on one of the most fundamental parts of networking: how a device gets its identity. Our mission is to unpack the Dynamic Host Configuration Protocol, or DHCP. This is the protocol that lets almost any device from your laptop to your car get online. It's like the network's automatic passport office. And when we say host, we mean basically anything, right? The definition is really expanded.
It really has. We're not just talking about PCs and servers anymore. Think industrial controls, smart vehicles, even the power meter on the side of your house. If it needs an IP address, it's a host.
And every single one of them needs 4 non-negotiable pieces of information to work on an IPv4 network.
That's right. They are the absolute essentials. First, its own unique IP address. Second, the subnet mask, which, tells it the size of its local neighborhood.
Its local bubble.
Exactly. Third, the IP of the default router, its door to the outside world. And finally, the DNS server addresses, so it can translate names like google.com into actual IP addresses.
And if any one of those is wrong or missing.
The host is basically a ghost. It might be there, but it can't talk to the internet or even other networks. It's isolated.
And you could run around and configure all these manually the old static assignment way. But DHCP really changed the game for IT. It's all about control.
Oh, absolutely. The efficiency is massive. Centralizing it means you cut down on user error, which is like the #1 cause of network problems.
I can believe that.
But it's more than that. DHCP gives us what we call address reclamation. A visitor connects to your Wi-Fi, their laptop gets a temporary IP address, and when they leave, that lease expires. The address goes right back into the pool for someone else to use.
And that mobility piece is huge, too.
It is. Think about it. You take your tablet from a coffee shop to the airport, then back to the office. DHCP handles all the reconfiguration in the background. New IP, new gateway. You don't even have to think about it.
Okay, so let's dig into how this actually works, because it starts with a really interesting paradox. How does a device with no IP address send a message to ask for one? It's like mailing a letter with no return address.
That is the perfect analogy. It's a classic chicken and egg problem, and the solution is this famous 4-step dance we call DORA.
DORA. Okay, so that's an acronym for Discover, Offer, Request, and Acknowledgement. Let's start with D for Discover.
The Discover message is the client basically shouting into the dark. It's a broadcast message that goes out to the whole local network saying, "Hello, is there a DHCP server out there that can help me?"
And if the server hears that plea, it responds with the O, the offer.
Right. And the offer is just a proposal. The server says, "Hey, I've got an IP address for you. How about this one?" It also includes the other stuff, like the subnet mask and the router IP, but it's not final yet.
So the client gets the offer and then sends the request saying, "Yes, I'll take that one, please."
Precisely. And that's an important step because there might be multiple DHCP servers that send an offer, and the client has to formally request the specific one it wants to accept.
And the final step is A for acknowledgement.
The ACK. That's the server making it official. It says, okay, that address is yours for this amount of time, and it hands over the final complete configuration. The client gets its network passport stamped.
Now, you said that first Discover is a broadcast, but for that to even work, it has to use 2 very special IP addresses.
It does. I mean, the packet has to have something in the source IP field. Since the client doesn't have a real one yet, it uses 0.0.0.
The I am nobody address.
Exactly. It's reserved for a host that's bootstrapping itself. And since it doesn't know where the server is, it can't send it to a specific address.
So it sends it to everyone.
To everyone on the local wire.
Yeah.
It uses the destination address 255.255.255.255.255.
The local broadcast address. And routers, by rule, do not forward those packets, right? That's what keeps the request from flooding the entire internet.
Precisely. It contains the chaos. And interestingly, the service offer also comes back as a broadcast of that same address because the client hasn't officially accepted its new IP yet. The client knows which offer is for it because its own MAC address is embedded in the message.
Fascinating. But what if it fails? What if there's no server or it's down? The device doesn't just give up, does it?
No, it has a fallback mechanism. It's called automatic private IP addressing, or APIPA.
The dreaded 169.254 address.
That's the one. If you ever see an IP address that starts with 169.254, you know instantly that the device tried DHCP, but the DORA process failed.
And with an API address, you can talk to your neighbors on the same little network segment, but that's it.
That's it. You get an IP and a default mask, but crucially, no default router and no DNS. You're stuck in your local cul-de-sac. You can't get out to the main road.
So that broadcast limitation really forces a big design choice. Do you put a DHCP server on every single subnet, or do you centralize them?
And for any organization of a certain size, centralizing is almost always the answer. It's easier to manage, it's cheaper, you have one place to control your entire IP scheme.
But then you have to get around the broadcast rule.
And for that, we need what's called a DHCP Relay agent.
So the router itself becomes a kind of helper, an intermediary.
Exactly. The router interface that's facing the clients, the one on the subnet without a DHCP server, gets a special configuration. It's a really simple but powerful command. IP helper address.
And you just pointed to the IP of your real centralized DHCP server.
You do. And the router then performs this bit of magic. It listens for those DHCP Discover broadcasts.
The ones going to 205.25, 5.25, 5.255.
Right, it catches them. Then, and this is the key part, it changes the source IP address in the packet from 0.0.0.0 to its own IP address on that interface.
Oh, I see. It has to do that so the server knows where to send the reply.
You got it. The router is effectively saying, hey server, this request came from a client on my network. Send the reply back to me and I'll handle it.
So it's vouching for the client.
It is. Then, step 3, it changes the destination address from the broadcast to the specific IP of the server from that helper command.
Which means it's no longer a broadcast. It's just a normal routable packet.
And that's how it gets around the rule. Step 4 is just routing the packet like any other. The whole process just reverses on the way back. The server sends the offer to the router, and the router broadcasts it locally for the client.
That's incredibly clever. So on that central server, what does the configuration look like? It must have to know about all these different subnets.
It does. You set up what are usually called scopes or pools for each subnet. You define the subnet ID and the mask, and then, very importantly, you define a range of excluded or reserved addresses.
Those would be for things you never want to change, like the router's address itself or other servers.
Exactly, the static IPs. And then you just fill in the options that the clients in that subnet need. What's their default router? What are their DNS servers? You can even get fancy and set up static assignments where you tie a specific IP address to a device's MT address forever.
So that covers all the user devices, the hosts. But what about the network gear itself? I've heard that switches and routers can sometimes be DHCP clients too.
They can. For a switch, it's usually just for initial setup and management. You can tell the switch's management interface, usually interface VLAN 1, to get an IP via DHCP.
Just to get it on the network so you can manage it remotely.
Right. The command is APIPA Address DHCP. And if you want to see what it learned, the best command is show DHCP lease. That'll show you the IP, the lease time, and the gateway it learned.
And a router? That feels really strange. Routers are supposed to be the static, reliable anchors of the network.
They are, except for one very common scenario. The router at the edge of your network connecting to your internet service provider.
So your home router or a small office router.
Exactly. The ISP doesn't want to manually manage a static IP for every single customer, so they use DHCP to assign your public IP address, your mask, and tell you the IP of their upstream router.
Okay, so when a router gets its DHCP info, does it behave differently than a PC?
It does in one critical way. When it learns the default gateway from the ISP, it doesn't just store it. It automatically converts that piece of information into a default route in its own routing table.
So it creates a route for 0.0.000 pointing to the ISP's router.
Precisely. And if you're ever troubleshooting, you can spot this automatically created route because it has a unique signature, an administrative distance of 254.
And that number is significant because...
Because it's a very high number. In routing, lower is better, more trustworthy. A static route you configure yourself is a 1. By making the DHCP learned route a 254, the system ensures it's the least preferred route possible.
So if you ever decide to manually configure a different default route, it will always win. It's a safety measure.
It's a perfect safety measure. It provides instant connectivity but preserves administrative control.
This is great. So now let's bring it back to you, the listener. You're at your computer, and you want to check these 4 critical settings. But first, we have to talk about something called subnet agreement.
Yes, this is so fundamental. Your computer uses its IP and its mask to decide if a destination is local or remote. If it's local, it sends the packet directly. If it's remote, it sends it to the default router.
And the router has to make that exact same decision.
The exact same one. If the DHCP server gives your computer the wrong subnet mask, your computer and the router will disagree on what's local. Your machine might try to send a packet to the router that the router thinks is local traffic, or vice versa. It causes all sorts of weird, hard-to-diagnose problems.
Which is why verifying is so critical. Let's start with Windows. What's the go-to command?
The first stop is always ipconfig. That gives you the big three: IP, mask, gateway. But for the real details, the DNS servers, who the DHCP server is, when your lease expires, you have to use ipconfig all.
Ipconfig all. Got it. And to check the routing table itself.
You'd use netstat marsIN. That will show you the default route and confirm that it's pointing to the gateway you think it should be.
Okay, what about Mac OS and Linux?
On a Mac, the old command is ifconfig. But it can be a bit tricky because it sometimes shows the mask in hexadecimal, like 0 oxcef 0.
Which is 255.255.255.0. Not super intuitive.
Not at all. A better command is network setup with the tech@info flag. And netstat arn works there too to show the routing table. You'll actually see the word default in the output.
And Linux is moving to newer tools, right?
It is. The old ifconfig and netstat are being replaced by ipaddress and iproute. And the output of iproute is fantastic for DHCP troubleshooting. It will literally say default via gateway IP proto DHCP. It tells you exactly how it learned that route.
That's super clear. So those commands lead us right into troubleshooting. What are the common failure signals we'd see?
Well, scenario one is that it's not using DHCP at all. You run ipconfig all on Windows and you see the line DHCP enabled. No. Simple as that. It's statically configured.
Okay, scenario 2. Total failure.
That's our old friend APIPA. You see an address starting with 169.254. You'll also notice the fields for default gateway and DHCP server are just blink. The DORA process failed completely.
And the last one, which sounds like the trickiest, is when everything looks like it worked.
Right. This is an incorrect DHCP server configuration. The client completes the DORA process, it gets an IP, it's happy. But the information the server gave it is just plain wrong for that subnet.
Like the default gateway IP is off by 1 digit.
Exactly. The server tells the client the router is at 10.1.1.254, but the router is actually at 10.1.1.1. The client will correctly send all its internet traffic to a black hole, and you'll be scratching your head wondering why it can't get online when its configuration looks valid. You have to compare what it learned to what the network design says it should be.
It really all comes back to those 4 essential settings: IP, mask, gateway, DNS. This whole deep dive shows how critical that simple DORA process is.
It's everything. And that's why, at the end of the day, almost any IP connectivity problem starts with going back to the basics. Go to the host, run the verification commands, and check those 4 things.
And that wraps our deep dive. We've seen just how vital it is for the host and router to agree on subnet boundaries, and how one small mistake on Essential Server can break things for thousands of users. So here's a final thought to leave you with. Given that this whole system of identity is built on trust, a client with no credentials just broadcasts a plea using 02 0 tets. Think about this. What stops a malicious device on the network from answering that broadcast first, pretending to be the DHCP server, and handing out fake passports that send all your traffic through them? That's where we cross the line from networking fundamentals into network security. Thanks for diving deep with us. We'll catch you next time.